Hello and welcome back. In this video, we're continuing our discussion of SN1 and E1 reactions, and we're going to do a comparison of some different effects that we can use to help determine how that reaction will go and what our products might be. So the first of those effects is the solvent effects. So the solvent can affect whether a reaction occurs faster or slower. And the type of solvent that's preferable for an SN1 and E1 reaction is a polar protic solvent. And we can see that here if we take T-butyl chloride and look at the ionization of it in different solvents. We can see that in water, or well, let's just say in ethanol, we have a relative rate of 1. Okay, in water, the ionization occurs 40 times faster. In methanol, it occurs 5 times faster than ethanol, okay, because ethanol is more hydrophobic than methanol, but not by much. And then in acetone, this is not a polar protic solvent. It is much slower, and diethyl ether is practically negligible, okay? So these are polar aprotic or just aprotic. Diethyl ether is not really very polar, only slightly polar. So the polar protic solvents are better at stabilizing the unimolecular reactions SN1 and E1. So we can see here that the polar aprotic solvents are better for SN2, and the polar protic are better for SN1, and that's because in the SN1 reaction, the carbocation forms faster, and we need to stabilize that carbocation formation because this is positively charged, and so the polar protic solvent is going to stabilize that. It's also going to stabilize the leaving group because that leaving group is going to have a negative charge. So we need to stabilize the carbocation and the leaving group by having that polar protic solvent. Okay. And the polar aprotic solvent is better for SN2 because we don't stabilize the nucleophile with that aprotic solvent. We don't form a solvent shell around the nucleophile that's going to raise the energy to break out of that solvent shell for the protic solvent versus the aprotic solvent would have a smaller activation energy. So basically for that, polar protic is better for SN1 and E1, and polar aprotic is better for SN2 reactions, or even E2 reactions. Alright, so for the substrate, we need a stable substrate for the SN1 and E1 reactions. We need something that can stabilize that carbocation. And the more stable the carbocation, the faster the reaction will occur. Here you can see we have a tertiary carbocation, a benzylic carbocation, and an allylic carbocation. So benzylic and allylic are resonance stabilized. Even though allylic looks like primary, this resonance stabilization, because we could draw a resonance structure by moving this double bond over here, is going to stabilize it enough that it's about as stable as tertiary. So allylic is going to happen pretty fast, and then benzylic is even more stable because we have resonance all the way around the ring. So these are the types of carbocations that we can expect to form for the unimolecular reactions. If you have a primary or secondary alkyl halide or substrate with primary or secondary leaving group, then this is going to be usually too slow to get SN1 and E1 products or solvlysis type products. Alright, and so if primary or secondary can undergo that type of reaction if you can get a rearrangement to give a more stable carbocation. So tertiary allylic and benzylic alkyl halides undergo solvlysis to give a mixture of SN1 and E1 products. So for example, here we're going to form this carbocation because this bromine is going to pick up and leave. So the carbocation is here. okay? And that's a resonance stabilized carbocation. We can draw resonance structures for that all the way around the ring. But this is water, so we've got an OH group adding. It's going to add where the carbocation formed in this case because it's benzylic, so that's very stable. Or we can pull off one of these hydrogens next door here and form this elimination product. So we can get a mixture of SN1 and E1 products for this reaction. So for each of these, identify which is expected to undergo solvolysis more rapidly in water and explain your choice. So for A, we have either we can form, bromine can pick up and leave, and we can form a carbocation here. And for the second one, the bromine picks up and leaves, and we form a carbocation here. So the left carbocation is going to be benzylic because we have these double bonds, okay? And the right one is not resonance stabilized. So the left one is going to form the product much faster. And the product for that one is this, okay? So for B, we have left versus right. The left one, if we form a carbocation, is going to be allylic. So we could draw a resonance stabilized. We can draw the resonance structure for that. Okay, moving the double bond over here. So it's allylic, so the one on the right for B is going to form faster. And for C, we have to consider whether chlorine is more stable than bromine, and I really didn't cover that discussion for my students. So I'm not going to discuss this one, but this is a matter of whether chlorine or bromine is more stable. All right, and so draw all the expected products for each of the following solvolysis reactions. This is a challenging one, and so I don't know if I gave myself enough space here. So let's look at A, okay? So we're going to do solvolysis reactions here. So that means that we're forming this carbocation. So what can happen? For ethanol, what are we adding? We're adding that OET, okay? If we do an SN1 reaction, so that's going to, so let's just go ahead and draw it. I don't have a lot of space here, so I'm going to go ahead and draw it in. Okay, or when we form the carbocation, we could pull off hydrogens from here, okay, from here, and from here. The ones on the left are going to lead to the same product, and won't matter. So let's go ahead and draw that one in. So we'll get this, which is the same as pulling off the ones on the bottom, okay. But if we pull off the ones on the right, we can either get, so all of these are products. We can either get, let me see. Well, actually, we don't have cis and trans because since we have two of the same on the left, then that's the only product we can get. Okay, so we have those three possibilities. All right, for the second one, we're adding OH because our solvent is water for our SN1 product. Okay, we're not going to get a rearrangement here because it's tertiary. We can also get the Hoffman product, and we can get the Zaitsev product. Okay, so those are our possibilities. Next, this thing. We can get OME, ME is CH3, so we can get that. Or we can get the elimination product, which only has one possibility. And that's this. We can't eliminate at the rings because there's no hydrogens there, and those are aromatic. They're not sp3 hybridized either, so can't eliminate there. All right, so for the next one, we have two hydrogens here. And we have three hydrogens here. So we can eliminate at either one of those positions. And so the chlorine is going to pick up and leave. We're going to form a carbocation here. Okay, so we can get, let's see, that's a chiral center. So we can get the OH added this way, okay? We can also get the enantiomer of that. And we haven't talked about why that is, but we're going to get to it. Oh, I didn't draw that right. Okay, and then we can also get elimination products. Now we can't eliminate on the ring. We can eliminate from these 2 hydrogens I drew, or the 3. So that's going to be which? This way. That's our Hoffman product. Or we can get this Zaitsev product. If we pull off, one of those, we can also get the. I'm sorry, I didn't draw my ring properly. We can also get the other Zaitsev product. And from a carbocation, it doesn't really matter. We don't have to have that stereospecificity, but that's not even a problem here because we've got 2 hydrogens anyway. All right, and so we can form all of those products. All 5 of those are possibilities for this problem. So I think I'll begin this next discussion in the next video.